Good afternoon. I want to change a little bit the dynamics because, of course, people know me as director of the Graphene Center, but people do not know much about. I have actually, in the last few years, I have not talked about theoretical physics very much because we have been so busy here setting up the Graphene Center. And in that sense, I want to talk about physics today and about interesting things about dichalcogenides that I feel they are poorly explored. This is one thing. And the other thing that I want to talk about is people have been talking mostly about single electron properties of these materials. And I want to expand the topic and discuss many-body properties of transition metal dichalcogenides, because these materials are not only rich from the point of view of electronic properties, structural properties, but also electron-electron interactions and many-body states and complexity. And this has been very almost not explored these days. And I want to talk a little bit about that because it's close to my heart, in fact. But before I want to talk about monolayer transition metal dichalcogenides, I don't have to repeat what you have heard already many times here. I just want to point out the flexibility, the interesting flexibility of these materials. So if you look at these materials, you have essentially two possible orientations of the chalcogen layer relative to each other. They can have, they can be in registry like this. So if you look from the top, you get this graphene-like structure that was discussed here yesterday. But you can have also, this is trigonal prismatic, but you can also have an octahedral structure where these chalcogen layers are rotated relative to each other. Okay? And as was discussed here many times, most of the electronic properties are determined by the metal ion. But in fact, if you change this, the rotation of the chalcogen layers, you actually can get very different types of ground states. So for instance, in the case of, for instance, TMOS2, you have a semiconductor. But if you look at, for instance, O niobium disulfide, you have a metal with several bands crossing the Fermi surface, crossing the Fermi energy. So this is a metal, this is a semiconductor. And if you have the same element, but you just change the structure, actually, for instance, niobium disulfide goes in, well, actually this is selenide, but it's the same story. It goes into a semiconducting state. And if you take this one and you rotate the chalcogen layers, you make it into a metal. Okay? So this tells me that the p bands, because it's mostly D, you know, these materials are D transition metals, that the p electronic properties of the chalcogen have a very important influence in the electronic structure. Okay? And in fact, you can imagine playing with this different structures in different ways. So this is already a knob to change the electronic properties if we can get these different structures of these dichalcogenides. So you can go from semiconductors to metals, and this is just from the single particle, single electron perspective. Okay? So if you look at bilayers, because we talked about bilayers here a lot, and in the literature you find this notation 2H and 1T. So this has to do exactly whether in these bilayers you can have trigonal prismatic layers on top of each other, or the other configuration on top of each other. So essentially, you can have those. In nature, you can have these two structures, equilibrium structures, right? But since we are now in the club of putting things on top of each other, we can imagine actually hybrids, right? So if we can exfoliate a single layer of these materials, as I said, the unit cell, you know, of these crystals are naturally bilayers. It's exactly like graphite and graphene. The unit cell of graphite is a bilayer graphene. Okay? And here the unit cell of these compounds is also bilayers. So we can imagine again exfoliating different structures, and now you can keep the same element, but just changing the chalcogen orientation. Now you can make a tunneling barrier, for instance, although you have exactly the same metal in between. Okay, so this is the kind of interesting game that you can play with these materials, and I think it's worth pointing that out. So now when you see the literature on this, and there's a huge literature, okay, and I'm going to talk a little bit about that too, on these dichalcogenides, when you see these 2H and 1T structures, now you know what they mean. So they actually start from this more basic monolayer orientation of the chalcogen atoms. So the semiconductor, so I want to talk about the work with Alexandra, who is seated here in the audience. So if you have questions about this, you can approach her later. So essentially, when you calculate, for instance, these are different dichalcogenides. This is titanium disulfide. This is tungsten disulfide. The interesting thing that you see, of course, when you have similar geometric structures, you get similar electronic band structures. Of course, the details are different, but the overall topology of the band structure is very similar. And one thing that we notice on these materials is that when you calculate for the semiconductors the electronic density of states, you have these huge peaks in the density of states, which is great for photoabsorption, because essentially it means that you can have transitions at certain energies with very high intensity. And this is coming from this band nesting, the conduction and the valence bands in these materials in certain regions of momentum space actually nest extremely well with each other. And that's what produces a huge peak in the conductivity. So Alexandra has calculated for other materials. This is zirconium disulfide as well. And when you compute, for instance, the optical conductivity, you see these huge peaks, which is due exactly to these band nesting structures that you find in the band structure. So this is quite interesting because we talked a lot about optical experiments here. Okay, so we can explore different structures, and from the band structure and looking at this conductivity, we can play with this and make devices which can operate better than traditional devices. Okay, so this is a quite interesting thing. So another, of course, there are certain disadvantages of working with the systems, and we heard about this here. So it has been quite hard to get very large mobilities in these systems, and this is because of substrate disorder or intrinsic disorder in material and so on and so forth. And one traditional way to overcoming this in traditional semiconductors is actually to produce donor and acceptor states that are easily accessible at room temperature. So essentially we have been thinking about this, how to get there, and actually it's not hard to imagine. So you can physically adsorb, for instance, atoms on top of the structure, or for instance you can exchange the chalcogen. Okay, so this is interesting because, of course, if most of the conduction is coming in the metal band, you hope, at least, that this kind of substitutions will not affect tremendously the mobility. Or actually, let me put this in a different way. You expect that if you dope enough the material, the disorder introduced by the introduction of these atoms will be weak compared to what you gain by increasing the electronic density in the material. Okay, so we have studied this. Now, an advantage. Yeah, this is interesting because I have not seen this in the literature yet. Everybody talk about semiconductors in 2 dimensions as being equivalent in some way to semiconductors in 3 dimensions. But there is one effect that it's different, which is the density of states effect. Okay, so in 3 dimensions, at the edge of a band, the energy goes like square root of energy. But in 2 dimensions, it's a constant. So when you do your basic semiconductor calculations, you see that the thermal factors that appear in front of the donor and impurity the number of electrons in conduction and valence band change. They change from to linear in T instead of T to the 3/2. Very, very simple one particle effect. Okay, it has nothing mysterious about it. Just comes from this change in the density of states. And the interesting thing about this is that if you look at the number of carriers in a semiconductor as a function of temperature, there is this region, this is for silicon, at which the concentration is constant with temperature. And this is very important for the stability of the device. Okay, because of this change in temperature in the thermal occupation factors, actually this region of constant number of carriers actually is much bigger than in a traditional three-dimensional semiconductor. So very simple effect, one electron type effect that I think might allow, for instance, to operate semiconductors based on these materials at higher temperature. Okay, so how to get to this donor and acceptor state? So again, you just have to look at this material, look at the chalcogen atoms, and then you look at the periodic table. So the chalcogens are here. So everything which is on this side is going to be, will create acceptor states. And everything which is on that side is going to create donor states. Very traditional semiconductor logic, okay, like we are used to do in 3-5s and so on and so forth. So we went ahead and calculate, for instance, the donor and acceptor states, for instance, for replacement of the chalcogen or for physical adsorption and so on. And you can see you can have for instance, lithium adsorbed on the surface of these chalcogens can create a very shallow states, or if you replace, for instance, sulfur by silicon, you can get very deep states inside of the band. So essentially, in the way you can manipulate donor and acceptor states in a traditional semiconductor heterostructure or a device, you can do here by doing these chemical replacements. Okay, so you can essentially look, for instance, the wave functions of these different states. You have more delocalized states, more localized states, depending on how deep these states are in the gap structure. So the message here is that we can do traditional semiconductor physics with these materials as well if we know how to replace these atoms by appropriately, like people do in the traditional semiconductor in technology. Okay, so of course, when you have a semiconductor or an insulator, for that matter, the many-body effects, and this is go back to what I was saying in the very beginning, the many-body effects are suppressed. Because once you have a gap in the spectrum, unless the electron-electron interactions or the electron-phonon interactions are bigger than that gap, nothing will happen. So this is why most semiconductors, especially wide-band semiconductors, from the many-body perspective, are vegetables. Okay? Except when, for instance, you excite excitons or tryons or whatever, right? But then you're accessing an excited state, right? So you're talking about many-body physics in an excited state. It's different from talking about many-body physics in the ground state. Okay, so that's why you don't hear much about many-body effects, except for magnetism in some insulators, antiferromagnetic insulators and so on. There is very little of many-body physics there. So, of course, metals traditionally have a lot of many-body physics. However, as you know, metals rust, right? And a 2D metal is even worse, because at least a 3-dimensional metal has a surface which can rust and protect the bulk. But if you have a 2D metal, you don't have a bulk, you just have the surface. So, so this is the big problem with dealing with 2-dimensional metals. They will rust immediately as you expose it to air. So this is why in this conference here, nobody is going to show you, as far as I know, data on 2D metals, because it's much harder to work with them than semiconductors. Semiconductors are more stable to air. and normal conditions. So, but they are much more interesting from the electronic point of view. And this is what I want to try to show to you, that the physics of 2D metals is quite extraordinary, especially in this class of transition metal dichalcogenides. So, of course, for the experimentalists, this is a challenge. You have to do experiments in glove boxes under argon atmosphere and stuff like that. Okay, makes everything much more complicated. But I think that it's a very good challenge because it will bring new physics. It will bring new ideas and new knowledge to this field of two-dimensional systems. So I want to talk a little bit about that because I find this topic quite exciting. So I go back many, many years, 1973. This is a very famous paper by Matthews. He was at Bell Labs at the time when Bell Labs was the place to be. And he was calculating band structures of these. And remember, these are bilayer systems. Okay? So these are these bilayers. And you see, this is 2H niobium diselenide, 2H tantalum disulfide. And essentially, you see, you have these bands crossing the Fermi energy here. So you have electron hole-like bands at the Fermi energy in this case. And if you look at the dispersion out of these planes, and this goes back to what Francois was saying before, these are very, very flat. So there is almost no dispersion in the bands in the direction perpendicular to the plane of these materials, okay? So this means that the conduction in the z-axis is much, much worse than the conduction in the plane. I'm going to show some data about that. So I want to review a little bit the data on this because I feel that most people do not know this literature. And it's a very exciting literature on its own right. So I want to review a little bit of that and show you the richness of physics that you have in these materials. Okay, so this is just band structure. So here's the, I'm going to show a few phase diagrams. So this is the first phase diagram. So actually this is temperature, and this is the ratio between the in-plane to the out-of-plane lattice spacing. And there are different materials here. So this is, I think, tantalum diselenide, tantalum disulfide, niobium diselenide, and niobium disulfide. And these are all the phases that you have. So usually, at high temperatures, these are all good metals. Then they have a phase transition into what's called an incommensurate charge density wave phase. I'm going to explain to you what that is. Okay? So this is a lattice distortion that modifies the Fermi surface. And then, eventually, they go into a commensurate charge density wave phase, okay, where the lattice of the dichalcogenide locks in into a very well-defined structure. And here, you see, the interesting thing about this phase diagram is that these materials superconduct. Of course, they don't have fantastic TCs, but they superconduct, and temperatures around 10 Kelvin or something like that. And there is an anti-correlation between the charge density wave and the superconductivity. Okay? So there is a competition in these materials. The material wants to be a superconductor, but the charge density wave is frustrating that state. Okay? This is competition. So the interesting thing in this, as you go to this side of the phase diagram, you are more 2D. This side is more 3D. So the in-plane spacing is either if the in-plane spacing is bigger or smaller. So the charge density wave dominates in the 2D limit. And that's what we expect when we look for these materials when we exfoliate to single layer. I'm going to show you. I'm going to show you what's happening in there. So this is one phase diagram. Another very interesting phase diagram is this one, 1981, pressure. So you can apply hydrostatic pressure. And what's seen in this is tantalum diselenide. You see lots of different geometric phases. Okay, this has to do with this charge density wave. So this charge density wave will go from a normal metal to an hexagonal phase to a striped phase to a commensurate in two different types of commensurate phases with pressure. Okay, this is a lot going on a single material. And then you look at the superconductivity and you apply pressure, and as you expect, Tc goes up. Okay? As you compress these layers towards each other, superconductivity stabilizes. Okay? So this is, this was done long ago. Not many people know about this data, but I find this quite interesting. And actually, this is the charge density wave. It was fully characterized by neutron scattering. So I've been saying this for quite some time. One of the big challenges that we have in two-dimensional materials is to develop techniques, experimental techniques, that can measure diffraction. Okay? So this is a big challenge because the samples are very small. Right? We're talking about films which are angstrom thin. So how you develop techniques that can measure, you know, structures. Neutron scattering is perfect. So this is a very famous paper from '97 where they measure, you know, the Bragg peaks due to the charge density wave. And this is the original Brillouin zone, it's hexagonal. And then you have these extra peaks here, meaning that you have a triple charge density wave. So it has 3 different wave vectors oriented at 120 degrees from each other. Okay? So the intensity, you can see the intensity of these peaks were very well characterized. And if you look at the phonon spectrum, so we talked about phonons earlier here, what you see is that in the undistorted phase at high temperatures, the phonon soften. This is how the phonon softens. But then when the charge density wave sets in, the phonon hardens. The phonon which is getting softened towards the phase transition actually gets hardened in the charge density wave phase. That's very unusual because usually you expect that you have full softening of the phonon mode at the instability point. It's not what happens in reality. Okay? There's something different going on here. Okay, so this is the neutron scattering data. So just to explain to you, so this is the relative phase between these wave vectors. Okay? In an incommensurate charge density wave, you always have a phase difference, which means that these 3 vectors, these 3 distortions are not locked in with each other. But then, for instance, you look here at tantalum diselenide, there is a lock-in transition at low temperatures, and now the wave vectors actually set with the same phase. Okay? There is what's called Phason mode in these materials, which has to do with the freedom that you have to change the phase around. Okay? So this has it's all very well measured in neutron scattering. And when you look at the distortion, so this was the proposal, these are actually the distortions, so it's a bit complicated to see. The distortions are all in plane. Okay? They don't see anything going out of plane. And the interesting thing is that it forms a 3 sublatus structure with broken inversion symmetry. So the crystal at low temperature has much lower symmetry than the crystal in the normal phase. Okay? So this is quite interesting because it means that you can have some new physics coming from that broken symmetry there. Okay? So this was observed very early on. So, and this is all happening in plane. So the out-of-plane physics is almost irrelevant for these materials. Okay? And actually, if you look at the stripe phase, because I showed you a stripe phase, what's a stripe phase? It's very interesting. It has to do with this phase difference between these wave vectors. This is tantalum diselenide. On cooling, you see the transition I was talking about. So you go through an incommensurate phase into a commensurate phase. But when you warm the sample, on the way back, it has a hysteresis. So 2 of the wave vectors lock in, but the 3rd one doesn't. Okay? So it's very interesting. So, and if you look, actually, this can be observed in electron microscopy. Very beautiful work done many, many years ago by Fung, okay, and company. So they looked at, this is 10 Kelvin, 90 Kelvin, 100 Kelvin, 112 Kelvin. So you see, at low temperatures, the system is more uniform. You have big regions where the phases are locked in. And then as you warm up, you see the striping of the material. Okay? So this means that the material is becoming electronically homogeneous. Okay? So this is a quite interesting effect that shows that the electron phonon of electron ion coupling in these materials has to be quite significant. And if you want to understand the physics of these materials, you have to understand that. Okay, so now more data. Okay, data which is very hard for us to get on two-dimensional crystals. This is the magnetic susceptibility of different materials. So squares is tantalum diselenide, triangles tantalum disulfide, circles niobium diselenide. And what you see in the susceptibility is that, you know, in the metal, in the metallic phase, in the undistorted phase, looks like a metal, really. So the susceptibility goes up, but then at the charge density wave phase, it drops. And different materials have different drops in susceptibility. Because these are metals, it's very easy to interpret this. Because in a metal, the spin susceptibility is proportional to the density of states at the Fermi energy. So that means that in the charge density wave phase, you are losing density of states. It's gapping. The system is becoming gapped. But you see, the suppression is not complete, in fact. There is no full gapping. The system is not becoming an insulator in the charge density wave phase. It remains a metal, but with lower density of states. When you look at the specific heat, you see something very similar. If you gap completely a Fermi surface, you expect the specific heat to decay exponentially with temperature, essentially because there is no phase space for excitations. But in these materials, all the data shows power law, decay of the specific heat in the charge density wave phase. So again, showing that there is a metal there, but it's not a conventional metal because the Fermi surface is responding in a strange way, okay, to this charge density wave. So this is also related with what was discussed today. This is data or resistivity in tantalum disulfide, okay? So you see, this is the out-of-plane resistivity, and this is the in-plane resistivity. So in the normal phase, they have linear in temperature resistivities, but when the phase transition kicks in, and this is how this little blip here is amplified here, so you have this jump in the resistivity at the transition point, there is a decoupling between the in-plane with the out-of-plane motion. So essentially, in the charge density wave, the resistivity out of plane is huge. So you see, this is the scale you can see. Here is 50 micro-ohm centimeter. This is 4,000 micro-ohm centimeter. So essentially, electronically, the layers become heavily decoupled. And look at this. Out of plane, the material becomes insulating. In plane, the material becomes a better metal. For many years, this was a mystery because I was telling you that the system is losing density of states. How can you have a system that is losing density of states become a better metal? It's counterintuitive, right? You expect that you lose density of states, you become a worse metal, okay? But that's not what happens in these materials. So very interesting data, you know, and this is from where? 1974. Okay, so actually, many people then started to look at the Fermi surface, and this is, again, old paper, but I think it's very representative. So you see, this is how the Fermi surface looks like. The band structure looks like at the Fermi level. So you have an internal Fermi sheet here, so this is a Fermi surface, and you have another one at the edge. So actually, at this time, it was theorized that the charge density wave was actually triggered by the nesting between these bands. Okay? When you have two Fermi surfaces with nest well in momentum space, the susceptibility for charge density wave diverges. And that can trigger this charge density wave transition. But at the same time, during more or less the same time, people realize that also very close to the Fermi energy, there are van Hove singularities, not very far away. So actually, many people thought that, you know, nesting of bands in momentum space is something very difficult to happen. Okay, it's very unlikely because you have to nest two curves, okay, which are, you know, it's very hard, but maybe it would be the case. Some people thought actually that the transition was driven by these van Hove singularities because there you also have a very large density of states. And actually, this would explain the contradiction between the susceptibility and the resistivity. Why? If you gap a region with very large density of states, the electron phonon scattering rate goes down very fast. So essentially, you kill the electron phonon scattering, but you keep the system metallic. So you can reduce the density of states, but reduce the scattering faster than you reduce the density of states. Okay? So actually, this was, at the time, considered a good explanation for why you would have something driven by van Hove singularities in these materials. In fact, Morris Rice, many years ago, when he was a young man, proposed exactly that theory. But the Fermi surface that they drew was very different. You see, this is a Fermi surface of the same material if the Fermi energy would cross these van Hove points. Okay? Clearly different from the previous one, because these van Hove singularities are 60 millivolts above the Fermi level. So, and the problem is that, you know, if this is true, if the van Hove is driving this charge density wave, then it cannot be a perturbative effect. Then you really need a very strong electron phonon coupling for that to happen. Okay? And in fact, this is photoemission data on the same tantalum diselenide. The interesting thing about this is that Peter Johnson in 2000 measured the bands close to the, you know, from gamma to K, gamma to M. And this was actually how I started thinking about this, because when you measure this RPS data, so you see the band dispersing here, it looks like a normal parabolic band. But the interesting thing for me is that the line width of these bands were anomalously broad. And when you look at the energy dependence of the line width, which is given by these lines here, you see that they are linear in energy. Okay? And this is not the normal behavior of a metal. Okay? In a metal, this has to go like omega squared, not linear in omega. Okay? And this connects with work that was done in cuprate superconductors, actually. At the time, that there is this phenomenological theory called marginal Fermi liquid theory, okay? That essentially it's based on this linear behavior of the line width. Okay? So some connections with cuprates, if you like, since Professor Geim is so keen to get room temperature superconductors. Anyway, but this is a possible connection there. Anyway, so you have to go back, and now you have to go into theory, okay? No escape, because you have to understand better the electron phonon coupling in these materials. What happens in a normal metal, forget about this complicated electron phonon Hamiltonian here. But what happens is this: an electron comes, it can emit or absorb a phonon, and is scattered by the phonon, okay? If you have a uniform system with a uniform Fermi surface, this process cannot depend on the position on the Fermi surface, because imagine, if I have a circular Fermi surface, it doesn't matter where I start. My final state has to end on the circle. So I can rotate this without a problem. So in normal metals, with isotropic Fermi surface, the electron phonon coupling does not depend on the position at the Fermi surface, only on the momentum transfer. This comes from the fact that you have in normal metals, the states are essentially plane waves. Okay? But we know these materials are not like that. They don't have isotropic circular Fermi surfaces. So you have to look at this with a little bit more of care. And this is something I did, 12 years ago when I was looking at this. So you can calculate in tight binding, for instance, which is the more extreme approximation for localized states, what happens. And what you find is actually that the electron-phonon coupling in these materials actually changes a lot around the Fermi surface. Okay, so this is the Fermi surface, this is the Fermi surface. So these lines here are called nodal lines. Because of interference between different angular momentum waves, you can find destructive interference of the electron-phonon coupling, or at least a tremendous reduction. So a big variation of the electron-phonon coupling in the Brillouin zone. Okay? So based on this, you see that the charge density wave order parameter, which is proportional to the electron-phonon coupling, has also to vanish. So that indicates essentially that the charge density wave systems do not have uniform gaps around the Fermi surface, that the gaps have to vary strongly around the Fermi surface. And that's very unusual. Okay? So the proposal at the time was something like this, that to be consistent with this data, essentially you have to have the CDW gap varying like this and changing sign around the Fermi surface. Okay? So this is a high angular momentum state. It's L equals 3. Okay? But the interesting thing is this, is that if you have this, in fact, you have Dirac electrons. So in fact, if you look from this paper I wrote in 2001, I proposed that in the charge density wave phase of these materials have to have nodal excitations, and they are Dirac particles, just like what you have in graphene. Okay? So in fact, this is actually data that was sent to me by Peter Johnson quite some time ago. So this is looking at the band structure above and below the charge density wave transition. Okay? Neutron, this is RPS. Okay? And what you see here is that along the gamma m direction, there is no gap opening. So the Fermi surface doesn't change when you go from the charge density wave, from the metal phase to the charge density wave phase. So this is a good sign. If you look at the gamma k direction, so gamma m, no gap. Now gamma k, actually 98 people have observed a charge density wave gap. Okay? So essentially you have a situation that a gap is developing in this direction, but no gap is developing in this direction. So exactly what I proposed in this theoretical paper. Okay, that would happen. And the interesting thing is that this is a big gap. It's 70 millivolts. Okay? When I proposed this for the first time, people asked me, are there other is there any other experimental evidence for this? Because I don't know if you know, but experimentalists are very suspicious of each other. So if you do RPS, you don't believe STM. If you do STM, you don't believe RPS, or something like that. There is a psychology there. So essentially, you have to prove that many experiments are consistent with each other. Otherwise, nobody believes you. So actually, I didn't have to do that because in '91, there is a beautiful paper by Hess. This is one of the first measurements of superconducting gaps. This was done in niobium, I think niobium diselenide. And what Hess did was to measure the surface of niobium diselenide with an STM. And what he saw is this beautiful S-wave gap in there. What people don't remember is that he actually measured. So this is from minus 4 millivolts to plus 4 millivolts. But actually, he measured from minus 100 to 100. And in fact, the density of states, it starts to drop, actually 70 millivolts before. So even before, this is essentially what this means, that the density wave is already producing a big reduction of the density of states, which is consistent with the susceptibility measurements. Okay? But the superconductivity still develops on top of the charge density wave phase, because the system remains metallic. Okay? So it's a beautiful example of that. So this little blimp on this big curve is this data here. And I know because I have very many friends who do STM, and they use niobium diselenide to calibrate their STMs, because it's such a clean metal, very nice. You cleave it, and it looks very nice. You can do lots of things with it. And you see it's interesting data, even something that sounds so basic now. Okay, so this was the proposal. This is the Fermi surface. So you have all these Dirac cones there. And we all know what happens if you have Dirac electrons. I didn't know at the time. This was pre-graphene for me. The density of states is linear in energy if you have Dirac particles. And now you have to explain how can superconductivity be born out of something which has a reduced density of states. Okay? Again, you know, these many-body states, they use the energy from the density of states for condensation. So you have to explain that. And the thing is based on this idea that you have a broken inversion symmetry. So when you have a broken inversion symmetry, what happens is that by symmetry, you are allowed piezoelectric coupling, because you broke the inversion in plane. Okay? So essentially, you can couple directly, say, the acoustic phonons to the electrons linearly like that. Okay? And the idea was that there is, and this is a bit exotic, because, you know, piezoelectric coupling in a metal should not happen because you have electrons to screen the electric fields. Right? Piezoelectricity means there are internal electric fields. So if you have electrons moving around, they will go and rearrange to screen that internal electric field. So how that happens? It happens because these are Dirac particles. These are not normal electrons. Okay? So then you can, forget about this. Essentially, you can calculate the RPS line width, which is related to the imaginary part of the self-energy. Forget about all this. But then you can actually do and compare with the RPS data, and it fits extremely well, this data. Okay? So now superconductivity. So to get superconductivity, you need these Dirac particles to pair. Okay? They have to form Cooper pairs. Okay? I'm not going into the detail of this theory, so you can solve the traditional BCS problem for Dirac electrons. And what you find, which is interesting, is the following, is that because you have a suppressed density of states, superconductivity can only exist above a certain electron-phonon coupling. Below it, it cannot exist. This is not what happens in BCS, in normal metals. In normal metals, if you have an infinitesimal attraction between the electrons, you get an infinitesimal gap. Here it's not the case. You need a critical coupling. Okay? So this ties these materials to another area of physics, which is called quantum criticality. Okay? So essentially, you have to overcome a certain critical coupling to actually get pairing. And if you compare with BCS, it's very different in a metal. BCS in a metal. Okay, so again, this would be the phase diagram if I have a two-dimensional system. Temperature, this is coupling, which is essentially electron-phonon coupling. Then you see nothing, no superconductivity up to some point, and then you would get superconductivity, but only at zero temperature. Okay? In two dimensions, at no finite temperature, you would have true long-range order in the system. Okay? But if you add the phase fluctuations, you can have vortex, you have a Kosterlitz-Thouless transition, so you can add vortex, anti-vortex pairs. You would have a quasi-long-range order, but not true long-range order. And then if you add 3D coupling, then yes, then true superconductivity can appear in the system. Okay? So in 2D, we would not see this TC, but what we would see? We would see the fluctuations of these order parameters at finite temperature. Okay? So these fluctuations at finite temperature would affect the way the electrons behave. Okay? In the system. Okay. So just related to the phase diagram that I showed you before, the suspicion is that tantalum diselenide is sitting exactly at the quantum critical point for that transition, okay? Where the charge density wave and the superconductivity are competing hand to hand to win the Fermi surface. Okay? Good, so that's it, what I want to talk about. So essentially, I want to of course, we have talked a lot about technology and using these materials for technology here, and it's obvious that there are many, many applications, interesting applications, but I also want to leave a message that there is also very exciting new physics in these materials as well. Okay? It's not just a question of devices, but it's a question of understanding matter in a different dimensionality with different strengths of interaction. So I think it's a very interesting playground, and I think that even from technological point of view, to have two-dimensional superconductors would be quite interesting. So, so with that, I want to finish here, and I want to thank you for your attention. Thank you.